Alright, welcome to the video on Chapter 8. Before we get started, I want you guys to grab a periodic table, or at least have access to a periodic table that you can look at it because Chapter 8 deals with it. And so I'll give you guys a few seconds to go grab one.
Science presents the elements of the periodic table.
There's hydrogen and helium, then lithium, beryllium, boron, carbon everywhere, nitrogen all through the air, oxygen so you can breathe, and fluorine for your pretty teeth, neon to light up the signs, sodium for salty times,
Magnesium,
aluminium, silicon,
phosphorus,
then sulfur, chlorine, then argon,
potassium,
and calcium so you'll grow strong,
scandium,
titanium, vanadium, and chromium, and manganese. This is the periodic table, no gas is stable, halogens and alkali react aggressively. Each period will see new outer shells where electrons are added, moving to the right.
Alright, so now you should have your periodic table. So Chapter 8, again, we're looking at electrons. And not only are we looking at electrons, but now we're focusing on them in their presence around elements. How are electrons around elements? What are they doing? It's really a continuation of Chapter 7. Like I said, at the end of the Chapter 7 video, Chapter 7 and Chapter 8 are very close together. And so there's two things that we use to describe electrons. One is an electron configuration. And the other was an atomic orbital. Electron configurations just show you the total number of electrons and what orbitals they're in, but it's usually in a list form. So it'll go 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, and so on and so forth. And then you denote the number of electrons that are up here. So for S, you can only have 2 electrons. So here's 2, and P, you can only have 6. 2, 6, 2. In D, let's see, you can have 10. Had to think about that one for some reason. And so this up here are the number of electrons. And so that's the electron configuration. It just tells us the number of the electrons. In class we covered it. We'll cover it again. The atomic orbital shows us where those electrons are within the different orbitals. So you have 1s, 2s, 2p, 3s, 3p, and we get 4s, which is here, and then 3d. I don't have enough to draw 5 spaces. But you guys get the picture. And then in Chapter 7 we said the reason why we have molecular spin or electronic spin or the spin quantum number is so that electrons don't have 4 of the same quantum numbers, and so one electron has a positive spin or plus 1/2, the other electron has a minus 1/2. And we said the reason with those quantum numbers we can pinpoint a specific electron in an orbital, and we know exactly which one it is. And so electrons help us describe elements. What we're going to see later on is how we can use these electrons to help determine patterns on the periodic table. But before we get there, let's go ahead and just do some practice doing electron configurations as well as an atomic orbital. And so we're going to do number 41A, and the reason why I wanted you guys to get your periodic table is because we want to start using the periodic table to help us determine what these electron configurations or atomic orbitals are. And so 41A, we wanted the full electron configuration for silicon. So we go to our periodic table, we see silicon has 14 electrons. We know from the off-ball principle, so off-ball principle says we have to start at the lowest level. The lowest level is 1s. We put 2 there. Well, we're not done with the 14, so we have to do a 2s. Well, we've used 4, we still haven't used all 14, so we go to 2p, which is a 6, 3s, which is a 2, so now we've used 2, 4, 10, 11, 12, So we're going to finish off with this right here, 3p2. And actually, if you look at the periodic table, we'll talk about the p block and the s block in the next slide. But Si is in the p block, and it's 2 spots to the right, and so it should end at 3p2. So again, just ways to check ourselves to make sure we're on the right track. So this is the full electron configuration. If I asked you for the full electron configuration, this is what you need to draw. But then we have the noble gas configuration. And so the noble gas configuration looks at these core electrons right there, and we can summarize those as the preceding noble gas. So in this case, it's neon. So neon is 1s2, 2s2, 2p6. So we can just summarize that section into neon, but we then have to add 3s2, 3p2. And when we start talking at the end of this chapter, or in a couple slides about valence electrons and why valence electrons are important, this is the reason why. And this is the reason why noble gas configuration is so important, because it helps us determine which electrons are the valence electrons. And so that's the electron configuration. Let's look at a different one. Let's look at number 43. And let's look at A. So 43A is we're going to do the full atomic orbital diagram, or the atomic diagram, orbital diagram, it's the same thing, for this element. The element we're going to have is nitrogen. So let's go to our periodic table. We know 7 electrons. Whoops. Let's erase that. 7 electrons. So we know, again, according to the off-ball principle, we start at the lowest one, 1s. We know we have to fill up each orbital with 2 electrons, or that means it's full. So here we have 2s. So we have 4. Now we have 3 left. We know 2p has 3 orbitals, or 3 different orientations. And so we have 3 electrons left. And that's how they have to be put in according to the Hund's rule, right? So we have the off-ball principle where it says we start at the lowest, work our way up. Hund's rule says that we have to fill a degenerate orbital with 1 electron in a parallel manner before we can go back and fill others in. And so this is nitrogen. Now, let's say I want to describe this electron right here. We can use our quantum numbers to do that. So, the principal quantum number for that electron that I have circled is going to be 2, because it's in the second sublevel. It's in level 2. It is in a p orbital, and so that is a 1. Now, what orientation is that p orbital in? Well, we have to remember our ML numbers from chapter 7. And so it'll be +1. And so then we have to look to see the molecular spin. Now this number here, for this electron right here, it does not matter if it's positive or negative. I just draw the arrows up, and so it's positive in my example. If it was -1/2, then it would just be pointing down. And so if I were to give you these numbers, you would be able to draw 1s, 2s, 2p, 1, 2, 3, and put this electron right there. And so, for practice, if you want some extra practice on this, I would recommend it. I would say do the ones, I would say do number 42. And so for 42, it says to do the full electron configuration. I would do the full and the noble gas configuration, just so you can get practice looking at the noble gas configuration and using your periodic table to help you with that. And then I would do number 44. And so you can do that by next Monday. So next Monday, let me quickly look at a calendar. next Monday would be November the 5th. And so by November the 5th, you guys should be able to do these different types of problems. Okay, so noble gas configuration, and any configuration really, all stems from the periodic table. So the periodic table is very important. It's laid out in a specific way. These two right here in blue, I don't know why I drew that, are known as the S block. So they end with an S. Here is a P block. They end with a P. D block ends with D's, and F block ends with F's. We're not going to really worry about F blocks because when you start getting up to F's, it's a little strange. However, again, on Pearson, I might just give you one just so you can see it. You can be exposed to it. So, what else can we tell? Okay, great, Dr. Bishop. We see the S block, we know it ends in S. We see the P block, we know it ends in P. What else can we say? We can also use the periodic table to tell us how many electrons are in that S orbital, or in the P orbital, or in the D orbital. And just by looking at which column you're in. So this is column 1, column 2, and this will be 1 for the P block, 2 for the P block, 3 for the P block, and so on and so forth. And it starts over. So you have 1. So this would be S1, S2, P1, P2, P3, P4, P5, P6, and then D1, D2, D3, D4, D5, D6, D7, D8, D9, D10. It also, if you ever had a question about how many electrons are in an orbital, look at the periodic table. 2 can go in the S, 2 can go in the S, 6 can go in the P, 10 can go in the D, 14 can go in the F. So everything is right here. And so let's look to see how we can easily do. So the other thing we need to look at is rows. So here's row 1, 2, 3, 4, 5, 6, 7. If you note, can you guys notice a pattern, or they call them periods, I call them rows, about the numbers and what they correspond to? For the S block and the P block, the row number, the period number, equals the N. So here you have period 2. So you have 2S1, 2S2, 2P1, 2P2, 2P3, 2P4, and so on and so forth. It gets a little tricky when you start talking about D block. So if you can look at the D block, and then you look at the period number, so for D, it's always the row minus 1. And that's what your N is. So in this case, it's on row 4, so it'll be 3D. Here it's on row 5, here it'll be 4D. This, without actually using this and practicing this, the concepts are sometimes a little difficult. So if you have any questions about this, please, oh please, come see me about it. So how can we use this to our advantage, right? Because that's what we want to use. We want to be able to do things relatively simply when we do these things. So let's do a noble gas configuration. Let's pick phosphorus. Alright, so I want the noble gas configuration for phosphorus. Here is phosphorus right here. Can't see the P. There's phosphorus right there. And just for the practice, I know you guys have already seen it, but I'm just going to cross that out. So the noble gas configuration is, you go back to the previous noble gas. For phosphorus, it's neon. And then what you do is then you start counting. 3s1, 3s2, so we put 3s2 down. We have 3p1, 3p2, and the block, because you have to count it, which one we're doing, it's 3p3. So if we erase it, that's what it is. So that's how we can use the periodic table to help us, to make sure that we're on the right track doing a lot of these things. So practice this, when you do the nucleic, or the nucleic. The noble gas configuration, try it this way. And if you're still having issues, please, please, oh please, come and see me. So, valence electrons. So there's two different types of electrons. There's the core electrons, and then there's the valence electrons. And so when we looked at silicon, if we back up here, whoop, I erased it. So if we looked at silicon, silicon was neon, 3s2, 3p2, because it's one to the left of phosphorus that we just did. I'm going to also write the full one. 1s2, 2s2, 2p6, 3s2, 3p2. So, the other reason why we do noble gas configuration is because it helps us determine what are the core electrons and what are the valence electrons. So core electrons are those electrons, which would be these electrons that are the closest to the nucleus, that will not participate in any binding that silicon will go through, will go towards. These are core electrons. They're held tightly, and they're usually not let go. These electrons, let's change colors. Oh, let's do blue. These electrons, however, are known as valence electrons. Valence electrons are free to be removed, free to be shared during bonding. And so how in the world do we know that what are the valence electrons? Well, there's two ways. One way we know that things are valence electrons is we can do the noble gas configuration. Everything in the noble gas portion is the core. Everything in the outside of that would be the valence. So silicon has 4 total valence electrons. 2 from the S, 2 from the P. But there's another way that we can determine this. Here's the easiest way to determine how many valence electrons are around an element. This is column 1. This is column 2. This is column 3, 4, 5, 6, and 7. So, column 1 has 1 valence electron. Column 2 has 2 valence electrons. Column 3 has 3, 4, 5, 6, 7. So again, use the periodic table to our advantage. So, to practice valence electrons, to make sure that we understand how to calculate those, I want you to do number 51. And I want you to determine the number of valence electrons, because it will be very important in things that we're going to do in Chapter 9. So again, Chapter 7, 8, 9 are all interrelated. They're all interdependent on each other, and so we need to make sure we understand these concepts before we move on. So, there are other trends in the periodic table based on these electrons and a variety of other things. One of the periodic trends that you guys will have to know, you will have to know how to compare 2 elements based on these trends, is known as the atomic radius. And the trend is, as you go down a column, you increase the radius. It becomes bigger. As you go across a row, from left to right, things become smaller. So an example would be fluorine is smaller than iodine and smaller than lithium. So as you go from left to right, the atomic radii decrease. As you go from top to bottom, atomic radii decreases. So why don't you do number 61? And all of these, again, will be due on Monday, November the 5th, because it's really easy, really not easy, because it's conceptually sometimes very difficult, but it's very straightforward. And so the more practice we get, the better we'll become. So why don't you do number 61, so you can just choose the largest atom from each pair. The other trend is what's known as ionization energy. Ionization energy is the ease with which an element will give up its electron to become an ion. One thing you notice, these 2 rows have a low ionization energy. And as you go across from left to right, you increase your ionization energy. And when we start talking about in Chapter 9 octets and ways to fill shells and do all this other fun stuff, this will all start to make sense. Just for now, no, as you go across the row from left to right, you increase your ionization energy, to whereas alkali metals, any metal has a very low ionization energy because it's easy to give up those electrons, whereas any non-metal, which is over here, oops, let's erase that, made my circle a little bit too big, where any non-metal has a very high ionization energy, especially the noble gases. The noble gases, it's really hard to pull an electron off. But as you go from top to bottom, you also know there's a decrease in ionization energy. That doesn't mean that it's really easy to do it. It just means that there's a decrease in energy. And as you increase your size, you usually decrease your ionization energy. And that's the relationship between those two. There's another thing too here called, you can have more than one ionization energy because usually elements have more than one electron. And so here you can look at sodium and magnesium. Sodium and magnesium have pretty low ionization energies. Obviously magnesium has a little bit higher because you're going from left to right, but yet it's still pretty low when you're comparing it to a halogen. So that's the first electron. And we know sodium usually becomes +1, but magnesium usually becomes +2. So removing that first electron is really easy for both. But then what you notice is what's known as the second ionization energy. How much energy is required to take off another electron? If you notice in sodium, it's really high compared to magnesium. Well, magnesium normally goes +2. To go +2, you have to take off 2 electrons. It makes sense that it's easier to take off 2 electrons of magnesium than it is of sodium. And so again, these are just simple trends that we see across the periodic table based on the electrons around these elements. The next to last trend we're going to look at is known as electron affinities. These are affinities of these elements to gain an electron. And then once they gain it, to hold on to it. If you notice, halogens have the highest negative energy. They want an electron. They need an electron. If you notice, metals have a very low affinity to their electrons. And we talked about effective nuclear charge and a variety of other things on why that is in Chapter 7, or at the beginning of Chapter 8 in class. But just know halogens, they really want an electron. They are very reactive. What you will notice is the closer you are to this, to a noble gas, the more reactive you are. It's a little weird thinking about that this being as close to this, but it's really close if you can think of it like a circle. If we were to circularize the periodic table, halogens and alkali metals will be really close to noble gases. They're the most reactive. And then the last trend that we'll see is just an interesting one. As you go from left to right, you become less metallic. So sodium is obviously a metal, aluminum is a metal, sulfur is a non-metal, chlorine is a gas. So as you go from left to right across the row, you become less metallic, but as you go down, you become more metallic. Nitrogen is a gas, bismuth is a metal. And so, just again, the characteristics of a metal, ionization energy decreases as you go down, which makes sense because you become more metallic. And so these are just some things that we can use a periodic table for. The last thing that I want to talk about, and the last thing are ions, right? Because we've talked about non-charged species so far, but now we want to talk about ions, right? So ions can change the diameter. If you make an anion, which is a negatively charged ion, you're going to decrease the radii. Sorry, I said that backwards. You are going to increase the radii. Now let's take a minute to think about that. To make an anion, you add an electron. To add an electron, you're going to make something bigger because you have to increase the orbital size and what orbitals you're using. So you're going to increase the radii. So then if we make a cation, which is a positively charged ion, you're then going to decrease the radii. And so we can change just the size of an element based on the charge of it, whether it's an ion or not. we can also change the magnetic characteristics of these ions. And so there's two things that we're going to talk about: paramagnetism and diamagnetism. So paramagnetism means that you can be magnetized, or in a magnetic field you move. Diamagnetic or dia means there's no attraction. And the reason why something is paramagnetic is because it has an unpaired orbital. Diamagnetic, by contrast, is everything is paired. So let's look at an example to see if something is paramagnetic or diamagnetic. And this is going to be number 67 in your book. So 67, we're going to write orbital diagrams. The only way you can know if something is para or dia is through the orbital diagrams. And let's look at chromium plus 3. So we have chromium 3 plus. So again, periodic table out. Let's look at chromium. Chromium is a transition metal in row number 4. And so it has normally 24 electrons. But we want to make it a plus 3. That's confusing. So if we want to make it a plus 3, then we have to remove 3 electrons. So now we have 21. So now we have 3 extra protons in the nucleus compared to how many electrons we have, leading us to a cation. So if you make a cation, you subtract electrons by this charge. If you make an anion, you add electrons by the charge that's on it. So we have 21 electrons. So let me go ahead and erase this, and I will rewrite it over here. 21 electrons. So again, off-ball principle, we have 1s, 2s, 2p. So we have 10 electrons. 3s, 3p. So there's 18 electrons. So now we have 3 more left. Oh, so this is going to be a little tricky. We have to remember the order with which things fill. Four s comes first. And so we are left with 3d. Now, transition metals are a little weird in how we fill orbitals. We'll talk a little bit about it in class, the 2 exceptions that you should just be familiar with. But again, Pearson, I'll give you some transition metals just so you can see it on an exam. I tend to stay away from them because they can be a little bit confusing. But anyway, we have 21 electrons. Right now we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 21. Are there any unpaired electrons in orbitals? Your answer should be yes. That's right there. Because of that, this is paramagnetic. So, for Monday, as everything else, I want you to do number 67, A, C, and D as practice. That way you can just start practicing, doing again atomic orbitals, as well as seeing if things are paramagnetic or diamagnetic. And so this is pretty much Chapter 8. Chapter 8 is all about the periodic table, electrons, how they behave, how we can describe things.